Thank you very much. Hello. Thank you so much for coming, all of you. It's amazing to see so many people. And I was really honoured to be able to come back here, because the work I'm about to show you now actually started here in the labs, when it used to be called the labs. It's changed its name since. And yeah, it's just really nice to be able to have an opportunity to share where I'm at, and hopefully also to use it to help to communicate to you what I'm interested in, and what I think might be a vehicle for you to help others be interested in similar things, if that's something you think that's interesting. I'm saying lots of vague things, but the problem is, right, so computing is super important. It's one of the most important things, but I think it's one of the most understood aspects in society at the moment. People really don't know what programming is. I mean, how many people here have seen a professional footballer? None of you. Not on television? Not seen a professional? You've not seen the World Cup? Like a few of you. Okay, right, maybe football's not your sport. Well, right, how many people, okay, let's make it more abstract. How many people have seen a professional sports person of any kind? There we go, right. How many of you have seen a professional programmer of any kind? Programming, do their job. So yeah, for a Cambridge audience, it's not that large, right? And so this is a problem. I think when people see and talk about programmers, they talk about the kind of programmers they've seen on the TV or on films. You know, we've all seen The Matrix and the things flowing down on the screens and cubes spinning around and all kinds of crazy mumbo-jumbo that looks cool, but really isn't what actual programmers do, and doesn't really communicate what actual programmers can do for society. And I think this is a critical thing. And also, and I'll talk about this quite a bunch, but business and programming tend to be very closely related. And what we're going to see here is actually that's a small part of what programming can be. It's very useful for business. You can get a job as a programmer if you want to, but you don't do sports at school necessarily to become a professional sports person. You do sports for many other reasons, and programming has the same kind of values. Like you can learn programming to become a professional programmer, sure, but actually that's not really why you do it. There's tons of other amazing reasons, one of which, I think, and this is what I'm going to focus on, is that you can use code to express yourself. And I think that's really a really important theme I'm going to come across a lot. And so that's not just using code to solve business problems. This is using code like you might use words to write poems. Now, think about that. Actually, that analogy is really important. Can you imagine a world where words, language, was only ever used for legal documents? Would that be a world you'd like to live in? You know? No plays, no stories, no to-do lists, no all interesting ways to express ourselves. They're all gone. It's all contracts. And currently in the world of programming, it's kind of like that. Most programs are kind of like contracts for business, executing business requirements. And I think it's really interesting to start to explore what other domains programming can be incredibly useful for. Now, I'm sounding like I'm saying all this is new, right? But if ever you look at anything in programming, you'll always find at least 50 or 60 years ago, people have done all this stuff in abundance. You know, and it's really there's a whole a set of research and interesting things to draw from. In my case, it's even back like 1840s. So this is Ada Lovelace, and she was a musician, although people actually tend to refer to her as a mathematician. She was both a mathematician and a musician, and she treated them both on equal terms. And she was working on old computers that looked like this. Right, that's a pretty cool one, isn't it? Look at that. Where's the screen? You can't zoom in, can you? And these computers, I mean, it's stretched to call it a computer, of course, but these machines were used to perform calculations. And so they were for numerical calculations. They were numbers, number crunching, primarily for business purposes. And she was working on these with a chap called Charles Babbage. And what I found really interesting wasn't that she could imagine what kinds of computations these could do, what kinds of value these machines could have for society. She was imagining the future. And she was looking at machines like that they were building, and she was writing in her diary, I need to open up my software. This is Sonic Pi, which we're going to talk about. I've got the quote in the software. In her diary, she was saying, supposing, for instance, that the fundamental relations of pitch sounds, it's all very fancy language, sorry, in the science of harmony and musical composition were susceptible such expression and actions. The engine might compose elaborate and scientific pieces of music of any degree of complexity or extent. So she was looking at these machines. Where has it gone again? Oh, I lost it. There we are. And imagining them to be able to make beautiful music of our imagination. And this is amazing. And we were there today, right? Today, with computers of today, we can totally do that. And we've been doing it for many, 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 many years. What I'm going to show you is what I've done is try my best to simplify it in a way that everyone can do it. And I've been using this tool to go into schools to teach computer science and not saying, let's do sorting algorithms, because I mean, that's actually one of the things that schools were trying to teach as an exciting vehicle for getting kids to code. It's like, who wants to do sorting? Yeah. Oh, that's okay. So if we want to apply to the kind of people like us, right, are you a programmer? Yeah, see, exactly, right. If you want to apply to the people who are already going to become programming people anyway, then sure, sorting algorithms are going to be great. But if you want to try and appeal to everybody else, especially the people who wouldn't necessarily associate themselves in any way with programming, I think sorting algorithms are probably the wrong starting point. And the other one was, another resource I saw for schools was give binary a try. Like it's some kind of like, once you've tried binary, you're going to be hooked on it for life, like addictive force. So again, I don't think these are exciting. I think Ada's had a much more interesting perspective, and I think that using the creative arts is an amazing way to explore programming. And what's so interesting is you can go from here, 1840, to here. Now this is an image of a sort of more like a traditional DJ, right? And this DJ is performing on the stage. They've got a big crowd of people dancing and having a great time. This is in New York. Now this DJ, she's called DJ Dave, Sarah Davis, and she's using the software I'm going to show you today to perform on that stage. And so this really is something that is actually possible for human expression. And these people here in this crowd, all of them will put their hand up when I say, have you seen a professional programmer? Because Sarah is a professional programmer. She doesn't do business apps. She's a DJ. But she earns a living giving tours, giving performances, showing people the creative abilities of code. It's amazing. So I think this is a really exciting thing. And you can actually see like an example of her performing here. Like the lights going, and this is code. This is a real programmer. This is not the Matrix. This is not some visuals which look fun that someone's designed. This is a real programming environment, an IDE for creation of code and music. And there she is performing. So this is, to me, is really exciting. So I'm going to spend the rest of the time demonstrating what you can do, showing you how to get started. But, I mean, some people are going to watch the video, so they don't have the advantage of being here. You have the advantage of being here, so please, please ask as many questions as you can. So throw questions at me as I'm going, interrupt me, and I'll try and figure out a way to answer them and take you on an interesting journey. Because otherwise, why aren't you just watching the video and staying at home and sleeping in your pajamas in bed, right? So the fact you're here is amazing, so take advantage of that and ask as many questions as you can. So this software was designed for schools initially to teach computer science. And so the goal was to be as simple as possible. It's entirely free. It's open source. So you can download it. Once you've finished this talk, and you're like, yes, I'm going to learn how to code music. You can download this for free, and it runs on a Mac, runs on Windows. If you have a Raspberry Pi computer, it's installed by default there if you have the default operating system. And of course, if you're a super nerdy Linux person, you can get it working on there with a bit of extra work, as is always the case with Linux. And then when you get started, this is the other problem. Like in classrooms, I hadn't been into a classroom for a long time, since I was in school. And I had forgotten how little time teachers have to actually do anything. It's amazing. Like the kids come into the class, and they're all like, and the teacher has to try and calm them down. Johnny, can you stop spinning on your chair, please? Like, Sally, can you get off the tables? All this kind of stuff goes on. And then once they've calmed down and they've got the attention of the teacher's got like 1 or 2 sentences to actually get them started. And if those sentences don't land, it's really hard to actually get their enthusiasm. So the question I have to you, the open question is, what is your 1 or 2 sentences to get kids excited with programming? It's obviously not give binary a try or have fun with sorting, right? But even then, like anything that's anything to do with complexity, anything that's hard is already a massive friction. So the goal with Sonic Pi was to be as simple as possible, provide an environment that looks a bit like Microsoft Office or Word. So it's just a text environment. I can write some words into this thing, and if they are the right words, it's going to make me some music. Don't think they're the right words. No, they're not the right words. That's okay because you have an error, and the error tells you, look, I have no idea what means. Fine. And so this is when you need to learn some basic language, the code for the system. And every programming language, every system has different words that mean different things. In Sonic Pi, the first thing to learn is the word play, and you can choose a number, like 70. You press the run button, and you get a ping. There we are. That's fun. And so this is a full program. It's syntactically correct. You can talk about functions. You can talk about abstractions. I'm not going into any detail about those things because this is not a hardcore computer science lesson. But again, there's lots of opportunities for learning here. And this number here, what does this mean? Like higher number, lower number. We're changing the pitch of the note, how high or how low the note is. And numbers are really cool for that. Numbers have this really cool property that they can go up and they can go down. They're countable. And so if you can map something which can go up and go down to numbers, then computers can really reason about those things. And that's one of the things that difference engine was doing. It was reasoning about the numbers. Now, the next thing to think about is what happens if we do something like this. This is an interesting program. Now, if you're going to learn Sonic Pi, and I hope you all do, the way to learn it is not to expect it to make good sounds, right? Just like if you were to pick up a violin, it's going to sound horrendous for 10 years. Hopefully with Sonic Pi, it's slightly less time than 10 years, but certainly initially, it's not going to sound like some kind of amazing composition or production. But what is important is to look at the code first and imagine what it's going to sound like in your head. Just spend a moment thinking about it, then press the run button and hear it and be surprised. Now, I'm saying this kind of a trick question because how this sounds is really completely dependent on what I told it to do. I know because I programmed it, so I'm cheating. But this is a really interesting opportunity to talk about a bunch of stuff. So when I press the run button, you hear them both at the same time. Now, in the early days of Sonic Pi, this actually played note 60, then note 72, as you might have expected if you're working at the top and working your way down. This is called sequential programming. But so fast, because computers are incredibly quick, that you couldn't hear the difference. It's a bit like when you have a sprint and you've got two people who might have won and you're not quite sure. So you get that special camera out to see whose nose is slightly ahead of the other person's nose to declare the winner. 60 would be slightly ahead of 72, but only just super fast difference. In this version of Sonic Pi, the one we're seeing now, which is really not just for schools but also for professional musicians, these are actually played exactly at the same time, sample accurately. This is really important. Timing is really important. So in Sonic Pi, if you don't talk about time, which we haven't yet, everything happens instantaneously at the moment you run the program. So there we go again. So right. So if we want to separate them out, we need to introduce one more command, and that's the sleep command. And now we have the ability to make a little melody. Now this is fun because at this point you have the ability to program any melody you've ever heard or ever will hear. You can program Tchaikovsky, you can program Daft Punk, anything with these two commands. Now, of course, there is quite a lot of limitations and restrictions. It's not going to sound necessarily very good with the beeping. The notes are all the same length. There's no expression. There's no nuance. But the core, certainly of Western music, is available with those two commands. And that's really a lot of fun. And kids will just write hundreds of lines of code, just play and sleep, play and sleep, play and sleep, and making their melodies. And this is a great starting point. So in terms of education, this was like my starting point. How do I get into a classroom, get something interesting, get them to make a melody, and also, importantly, get them to create their own melody. Rather than say, this is what you need to copy off the board a melody and make it run. What is the note you would like to play? Did you like that sound? Was it too high? Was it too low? Did you want more notes? And then you would program your melody. Now, of course, I could stop here and say, that's it, you're done. Right, go off and make some cool tunes. But obviously, we've got another 40 minutes. And so it's important to spend the rest of the time, really, I think, taking you from here to here. right? Because obviously there's a big difference, right? She's not on stage going, boop, boop, right? That's not, no one's going to go and see that, are they? So they will all leave straight away. So the question is, like, how do you take this from here to there? And really that's just about a matter of learning or thinking about what it is you'd like to do musically and learning the code to make that possible. So the more interesting things you want to do musically, of course, the more code you're going to have to write, and different kinds of code. And we'll show you all of those things. But any questions at this point? No, you are happy with the boop boop. That's it, you're good, you're good. Did you want anything else more than boop boop? What did you expect? There's this, we've got a question in the back, hello. Can you do loops in Sonic Bank? Good question, we'll get to that very shortly. Yes, you can. Yes. Any more questions? Anyone see where to go? No? Okay, right. Loops is a good question. So, let's do the loop. You start a loop like this, and then like this, and you can do... There we are. And so this is just playing the same note again and again and again. Pretty exciting. It's more exciting, to be honest, though, if you swap out play for a sample. This is a pre-recorded sound. So you can take any recorded sound that you can find. So you can buy samples off the internet. You can take your recorder and you can record your own sounds. There's a bunch of built-in sounds into Sonic Pi just to make it easy for me to do demos like this and to give workshops. They're all what's called Creative Commons Zero license, so there's no issue in terms of copyright, so you're free to use these samples. Have a bass drum, and it's spelt in a German style because that's fun. And then, now we can hear now that this subwoofer and this labs aren't that great. So when I play this program in a cinema, it sounds poof, poof, or in a nightclub. I performed in a nightclub in Berlin. That was amazing bass. That sounded amazing. So you can start to test the quality of your headphones, your speakers, using the system. Now this is quite fun, right? So we have a kick drum. Now what happens if we want to, we can go a bit faster by sleeping shorter time. Sounds a bit nicer. We can make it a bit louder by increasing the amplitude. Amp is an option that we can add, so we can start to add a bit more code. It's important to point out at this point, I'm going to go quickly off in terms of what you can understand, probably, because you've never seen this code before. Don't expect to understand everything I write. Just recognize, and this is really important, that everything I'm showing you, I can and have taught to a 10-year-old child. So the only thing is time and patience and recognition that there is a huge gulf of difference between what's complicated and what's unknown and yet to be discovered. And sometimes when you see something new, you might actually think it's really complicated and it's just something you haven't yet understood yet. So just bear that in mind when I'm showing you. Now, this is fun because I can do something like this. Let's comment this out. So this means that the code is ignored. And let's do another loop. Let's do get a sample. Let's do what I don't know, like ambi-choir. Let's make it low rate. So we've got this rate is fun. I'll show you that in a moment. But this is something that kids would write really quickly in a workshop, and they would write this. So it's taking a loop, so I'm going to go a bit further than this, right? So now again, so this is an opportunity to look at the code, imagine what it's going to sound like. We had the choir, we had the kick drum, bump, bump, bump. So we're going to play them both at the same time, right? So let's go. Oh. Where's the kick drum? You've got to answer, yes. Because it says end here. Well, that's close, yes, because this end matches this do here. So this loop is, this loop, the first loop, runs across all of this code here. Yes. And you got an answer there? The loop never ends. Absolutely. There we go. This loop, this first loop, and between the do and the end, as you correctly pointed out, will spin around forever and ever and ever and never get down to the kick drum. Now, which was really sad for me because I was working in a school and we were teaching introductory computer science. There was a new computer science curriculum. The teacher was super excited. We were doing all new stuff. And we were spending time learning about what we could teach and then changing the software to teach the next lesson. And one of the girls in the class had done this, essentially, with different sounds. And she put her hand up, and she said, and I went over, and she said, I can't hear the drums at the same time as the bass, or the kick drum at the same time as the sample. Like, why not? What have I done wrong? And I looked at it, and I was like, okay, yeah, you've got an infinite loop there, and so that's always going to go around forever, and you'll never hear the second loop. And she looked at me like a bit puzzled. Like, well, that's a bit rubbish, she basically said, because obviously she's expecting it to be a musical instrument. And a musical instrument that can't play the drums at the same time as the bass, it's pretty rubbish, really. Like, why would you do that? And so I was like, okay, I know how to solve this, but we can't do that today because we need to change the system to introduce some new ideas. And I went to the teacher and I said, it's a really cool idea to play the drums at the same time as the bass. Can we do that? And the teacher said, that sounds cool. Well, question, yes, question. If you put spaces like this,
no, before end.
Like this,
No.
like this.
Yeah.
Oh, well, actually, it'll automatically tidy it for you. So that actually the spaces don't matter in this language. Well, good thinking, I like it. But yeah, so she, the teacher said to me, that sounds great, the drums sound the bass, they'll really like that. And then she said, is it on the curriculum? So I looked at this document, and it's got like sorting algorithms, and it's got conditionals, and it's got all sorts of stuff, algorithms, whatever they are. And of course, it didn't have the critical thing we need here, which is a really interesting idea. It's called concurrency. Now, concurrency, when you speak to a programmer, they go, oh, sounds complicated, can't do that. Right? Because it is kind of quite complicated if it's certain kind of situations. But in a musical situation, in a band, what's more complicated? Like the one-person bands, where one person is playing the kazoo and the guitar and the cymbals between their knees, and they're like trying to play all the instruments at once, or a band of like one person playing the guitar, one person playing the drums, one person singing, one person playing the kazoo. It's a funny jazz band. But, you know, like, so in a musical situation, having multiple band members is the sensible solution. And having a single person trying to attempt to play all at the same time is a comedy act, almost. It's like, why would you do that? That's crazy. In programming, weirdly, concurrency is seen as the hard thing, and just one person doing everything is seen as the easy thing. So this is a problem where we want the drums to play at the same time as the bass. We want the choir sample to play at the same time as the kick drum. And so we need the concept of concurrency. So we can say, I'd like essentially one person to play this and the other person to play the other thing at the same time, off you go. So I said to the teacher, I'm sorry, concurrency is not on the curriculum. And so the teacher said, sorry, yeah, we can't do that then. So I went back to this girl and said, I'm really sorry. You're going to have to, if you want to play the drums at the same time as the bass, you're going to have to wait till you're 18. You know? Because when you're 18 and you still want to do it, then you can come to a place like this and they'll teach you concurrency. Right? But we're sorry, it's too advanced for you at school. And she was actually quite distraught about that. She just switched off. She looked out of the window. She wasn't interested. What kind of rubbish kind of system that can't play drums at the same time as the bass? Ugh. And so that was really, for me, that was a depressing scenario. And so this is like interesting from a programming perspective, because as programmers, we get to redefine the world of computing all the time in ways that we want to. We have incredible creative powers to design new languages, to create new words that have new meanings, that can then affect people in interestingly new ways. And so in this situation here, I knew that the teacher wanted to do loops, right? Loops were on the curriculum, for sure. So that's good. Got that ticked off. But the kids wanted to do the two loops at the same time. So how do we solve that problem? Well, so either we can just say, no, sorry, you can't do that, which is what the teachers wanted to do, because it was obviously the easy choice. Or we could use our programming skills to say, well, do we have to finish at loop? Like, is the standard loop the final position? Or could we imagine a new kind of loop? Of course we can. So in Sonic Pi, I created this new kind of loop called the live loop. Sounds cool already, right? So there we are. And live loops need to have two things. They need to have the word live loop, obviously, but they also need to have a name, right? So here is Sally, and here is Kate. And so now we have these. If they have the same name, it's not going to work. So my band has a constraint. It can't have two Petes, because it's going to get confused, right? So everyone's going to have different names. That's okay. And now I've got them as different names. They play at the same time, right? So this is fun. So in schools, right, you don't teach loops in Sonic Pi. They don't exist. Shh. They're live loops, right? So the teacher thinks they're doing normal loops. Ha ha ha. You know, but the kids can play the drums at the same time as the bass. And this is a critical thing. And live loop I was just excited about this, right? This is important. It's the ability to be able to sort of sneak things under the hood, but also provide interesting tools. It actually turned out to be a critical part of the design of the system. So most of the interesting features that I've added to this, and I'll quickly run through them, weren't added to teach computer science. They weren't added because they're on the curriculum. Because if I adhered to that strictly, it would be boring and dry and not interesting, and it would tick all the boxes, but no one would go home, as you're all going to do, and go and play with the system, right? Because that's the goal. And it turned, hey, question, yes? Oh, so this programming language has, different programming languages have different ways of describing the scope of something, where something starts and where something finishes. Another way of describing that is kind of like a lexical closure. It describes the start and the finish. So in this language, this live loop, we're saying it's a live loop, right? That's introducing it. In fact, we're going to do a live loop. Then we have a name called Sally, and that's the name of the live loop. And to the people listening at home, the question was why we've got the end at the end of the loop. We then have a do to say whether the loop starts, and then we have an end to say whether that loop ends. So some programming languages do that by indentation, so that if you push it to the word to the side, that makes sense. That's kind of tricky, and they've got invisible things that are actually infecting the program in ways you can't see. I feel this is a bit clearer. If you're using something like Scratch, that programming language, you'll have a big box, big coloured box describing where the start and the end is. So just the word end lets you choose, that matches this. So this whole bit of code here is what's going to be in the live loop. That's all. So that end is required to match the do. And if when you program, you'll often find you'll actually miss an end out, right? And it won't work. And so it's like, oh, okay, where's my end? And you'll add it in. So it's an excellent question, thank you. So we are. Let's start live loop going. So, where were we? So we've got now the ability to play the drums at the same time as the bass. We're sneaking this under the hood. And also, yes, so many features are added into Sonic Pi, not just to teach the computer science curriculum, but it turned out that building this piece of software to focus on the computer science curriculum in schools wasn't that hard, actually. The hard part, the really hard part, was how on earth do we get kids to engage? How do we get them to be interested? How do we get them to be motivated to carry on, to want to do this? Not because we say, it's classroom time, you must do this lesson, it's what we have to do. Okay, sir, okay, miss, okay. We don't want that. We want them to go like, yes, doing music coding today, and that's what they're doing. So many of the features inside Sonic Pi were designed to help kids maintain that engagement. And there were musical ideas and production ideas that I snuck in, but all the time ensuring they didn't get in the way of what I've shown you so far, the basics, the building blocks of programming. And for example, one of those questions would be like, I want to be able to make a sound really big. All right, that's a common thing. So if I have a sound like, let's think about this. Let's go for the drum again. Sample, bass drum, house. Make it loud. I want it to sound like it's in a big room, right? The kids often ask this kind of question. Or I wanted to make it sound distorted. Or I want it to echo. Or I want to make it sound like it's crushed in a weird way, you know? And so in Sonic Pi, again, this is your do and end thing you're mentioning, we have a do and end, which is this lexical closure that describes the start and the end of some kind of modification, some kind of effect. And in this case, we're using an effect maybe like the reverb. And if I change the room size to 1, it's a big cave. So, and you can wrap this reverb do and end across any of the code. You can tell your entire composition, any line of it, any subsection of it. You just stick the bit around that you want to sound roomy, and it'll sound roomy. Or if you want to have it with an echo, you just use the echo command. Yes, question, hello. Does the amplifier go negative to make it quieter? That's an interesting question. I would have imagined that a negative amplification would just be a inversal of the phase. I don't think you could have a negative amplitude, but we can try. No, I've actually taught it, as I've forgotten I've even done this. Sorry, you can't do that. So this is the thing, right, in Sonic Pi. Give it a go. If you've got a question like that, throw it in, and if the system knows that that's not a good move, it'll let you know that. So you're free to do whatever you want. And I mean, I won't show you now, but you can try your best to make it as loud as possible. And obviously in the early days, that was made the headphones really loud. In schools, it's not great. So I've added limiters and compressors to actually safety systems to reduce the volume. So you're free to try any numbers and see what happens. And it's not going to it might sound horrible, but it's not going to blow your ears off or make your speakers explode or something like that. Which is, that's an interesting thing. So, good question. Any more questions? No? Cool. So, I'm going to spend the rest of the time now moving on from computer science and talking about music, but in a way that actually uses the computer science to do the music. This is the interesting part. And this is getting us over to here. So, samples are really interesting. Samples are pre-recorded sounds. We saw earlier that we could use this what was it called? Ambichoir. That's how it sounds normally. Let's make it a bit louder. Now we saw actually there was a rate option. These options that you can put the comma, the name of a word, and then a value. These are extra options you can just start to then modify and control your sound. And they're actually no different from, where did I have a picture of synthesizers? So you have these synthesizers, these knobs and twiddlers here. These have all got names written on them. And the value of the knob is the value of the thing that's controlling. So one might be amplitude. And so you can go up to 10, but you probably can't go to minus. It probably isn't you can't go reverse on the knobs. But there'll be like reverb and maybe distort, all sorts of different kind of knobs. Each synthesizer has its own set of controls to modify and manipulate the sound. And in Sonic Pi, this piece of code here, the sample, actually, this is the actual executional model of that sample. Now, I expect you all to understand that completely. But what's important is each of these little weird blobs connected by wires is a little individual piece of code which is executing, and this is all executing audio rates. Audio is flowing through the system, and all the black ones, they're the knobs. They're the knobs that you can control. And so you do not need to understand this, and this is the cool thing about computer science, is we can take complex things like this, which I designed this, spent ages designing this thing, and now I can't remember how it's built because I don't need to, because I've used something cool called an abstraction. And that means I can then take this complicated thing and wrap it up and just see this word now. I can just see sample now. Whenever you see the word sample, whenever you hear that sound, what's actually happening behind the scenes is the computer is making one of these things, playing the sound, and then destroying those things. Some cool stuff happening behind the scenes, but you don't need to know about this, right? This is the fun part. And this amplitude is one of those black knobs. And this rate is also one of these black knobs here. So you can start to control all these things. And there's documentation for everything. So if you don't know what's available, you can read and you can learn. Now, rate is the fun one because I can control how fast the sound is played, and it changes the pitch. So I can, by just changing the rate, I can start to make these like choir boys into monks, which is pretty fun. And you can do that with any of the sounds. So here, let's try this one. This is a good one. This is a drum break created by a band called the Winstons in the 60s. And this guy's beating the drums, and someone recorded it. And then it ended up getting passed on to a CD, sampler CD in the 80s, which was then given to producers. And then they started to use this music in their work. And it's pretty recognizable because a whole ton of genres of dance music were created basically off this one sample. And there we are. One of the early uses of it was Dr. Dre in the 80s. He used this, he played at half speed and rapped on top of it. So one of his early NWA tracks, you hear this. Imagine rapping on top. And of course, in the UK, we were like more into our sort of fast drum and bassy stuff, so we played it at rate 1.5, so that's going to be faster. We know where we're going with that, right? So this is interesting. With one sample, we can start to mess around and control it. Now, where you can take this is really interesting, because what happened with the drum and bass scene particularly is they were taking samples like this and doing interesting things with them. They were using magical audio scissors to chop up the sample so that each individual drum was like a single drum hit, and then they were then stitching it back together in different orders. So it's a bit like getting a newspaper, chopping all the words out, and turning an article that's about whatever, A, and turning it into something about something else, and making your own article out of the original words. And so you can do the same with this. And again, this is like a critical problem of, I can imagine building something that does this, but could I imagine teaching it to a 10-year-old child? And this was always like a funnel that all the design went into. Like, it's not just a question. Hello.
If you don't set the value of amp or rate or any of the other things,
Yes?
does it have default values?
Yeah, absolutely, absolutely. So if you don't set the value of rates, it has default values, absolutely. And that's why you can get away with writing this, and it still works. So it's just a bit quieter, because it's at amp 1, and it's at rate 1. And you can look at the documentation for sample, and it will tell you somewhere what all the options are down here, and what the defaults are, and what the ranges are. And so you can start to learn and play with them. And sample does loads of cool stuff. It's really fun. And one of the coolest ones is, what I talked about now, is that I wanted to be able to work with, let's make it louder. So now what I'm doing, I'm using a number again, but not to choose the pitch, but using a number to choose where in that sample, which drum I'd like to play. And here we're playing the 6th drum. Now it says 5, and I've said 6th. That's because often in computer programs, we start counting at 0. Just the way it is, right? You've got to accept that. Yes, hello?
Is it possible to set a function around amplitude to actually vary the amplitude?
That's a very good question. Is it possible to vary the amplitude as you're playing it? Yes, it is. Absolutely. You can create when you trigger a sample, you can grab a variable representing that sample, then you can send control messages to it later on to modify any of the control parameters. Some of the control parameters you can't modify, and the documentation will say which ones you can't. But yes, absolutely. So what's fun here is I've actually used these magical scissors. A question back there. Hello. So the question is, from an educational perspective, is it possible to display the actual note? No, because it's not really an easy thing to actually extract from the audio. Here in this example, what is the note of an arm end break? It doesn't really exist. You could imagine, if you're doing just the general play stuff, having also the sending to another system which notes you're playing, for it to render it, for sure. But no. I mean, but also the display of which note you're playing is kind of in the code itself. So in the same way that, would you say the same for a composer composing a piece of music in the traditional Western sense of having a stave and the dots? That's a representation, visual representation of the composition. Do you need another representation of that? No, that is it. And they're actually quite similar.
I just wondered how the frequency values relate to...
That's a really good question. Okay, yeah, just quickly look at that. So if I look at this, what is the units of this? You're asking. So this is an important question. So the units of 70 is what's called midi, and they map on to Western tuned notes on a piano. So it's kind of like the 70th note on the piano. It's not quite, it's offset like by 22 or something. But each integer up, each whole number up, is a whole semitone. And so you can hear that, and it's all tuned in like a scale. I'm going chromatically up through all the white and the black notes in the piano. But interestingly, I can do this. I can play notes in between notes. So this is like a guitarist bending the strings, or a violin player just moving slightly off the actual position of the note. And so, again, here, like this, there's no clear Western notation equivalent of this. But here we're into interesting microtones, and we can play drone music and all sorts of interesting things. We're not limited to Western notation, although it's the default. We were able to really do all sorts of interesting things in terms of both time and pitch. But really good question, thank you.
Can it sing?
Sorry?
Can it sing?
Can it sing? Can the software sing? If you record someone singing, then you could play that as a sample, for sure. In fact, I probably have an example of that built in. I've got some samples. So if I have like a CR2 lane, I think it's called. These are samples I used to perform with, and I think like number 2. No, which one is it? Excuse me. It's, lanes, plural. I need to remember this. Oh, no, that's not S. So yeah, it can sing. But this is not software singing. That's somebody else singing that's been recorded, and the software's playing that recording back. So essentially, any sounds that you can record, you can play back with the system. Yeah. Yep. Any more questions at this point? No? Cool. So, where are we now? So we were talking about the Amen break and loop Amen, onset 0. So this is the magical scissors, and what it does is it finds each individual drum hit and associates it with a number so we can work through the sample. And this is fun when you combine it with loops. Remember, loops in Sonic Pi are not called loops, they're called live loops. They're way more fun. And I can now play that loop again and again and again. Speak a bit louder. Maybe shorter. Maybe. Now I can work between different notes, or I can randomly choose one. It's starting to get interesting, right? So what we've got there is we've got an interesting case of randomization. We've got loops, but what you didn't notice probably is that programmers might notice is that as I was working with that, I was changing it whilst it was running. Did you notice that? I made it a bit louder. I switched the notes around so I can get it running. I'm going to make it quieter. Make it louder again. Make it a bit quieter. I can even change it to a different sample. Like this. And it's all in time. Another critical part of Sonic Pi that wasn't for schools, that wasn't for teaching the computer science curriculum, but was really important is the ability to be able to modify the code as it's running. This is called live coding. And this is where Sonic Pi stops becoming just a composition tool, because you can hopefully imagine yourselves writing play, sleep, lots of samples, some effects like the reverbs and distortions, and there's lots of effects in there to make a composition. That when you finished it, you go, I'm pleased with this, and you press the run button, and you show it to your friends, and they can hear that, and that's great. And then you can copy the code, and you can paste it in an email, and then someone else can receive it, and paste it into their version of Sonic Pi, and they will hear the same music too. So you can use the code as a way of sharing the music. Yes, good question, yes?
In like a piece of code that returns an error, will it like stop playing, or will it just...
If you have a piece of code that returns an error, will it stop playing? I'm going to answer that question, but in 2 minutes. It's a good question. I will cover that. And so you will be able to share the composition just by sharing some words. And this is a really important thing. But here, what we're doing now is we're actually modifying the code as it's running. And so we're turning this not just into a composition where you have the same piece of code producing the same music, into a performance where you have a small piece of code just running around. And if you left it, it would be pretty boring. Like that would be pretty boring after a while. We would all get a bit bored of it. But what you'd instead do is you slowly modify it and modify it and modify it and keep changing it, and it keeps being interesting. And so you could improvise music with this approach. Now, what's interesting is that so this is a critical thing. So adding the ability to change the code as it was running, not on the computer science curriculum, but really useful for engagement, and also in a way that doesn't interfere or hinder the teaching of the basic computer science curriculum. But another question was, another aspect is when you make mistakes. So if I have another live loop, and I'm going to do like bass drum house, seat for half a beat, and let's make it like, they're really in time with each other, and I'm coding like having fun, and I'm like, I'm going to make a mistake. So I'm a bit stressed and nervous, so I run the code. So that might answer your question here. So I made a mistake, and the live loop that has a mistake has stopped, but the live loop that doesn't have a mistake keeps going. So this is really useful. So if you're ever performing with Sonic Pi, make sure you have at least 2 live loops. Because when you make a mistake, and you will make a mistake, you can't avoid it. You can't ever be 100% perfect. Then the audience will think, they've reduced the sound down to something simple. And you're like, oh no, I've broken it, and you can fix it, right? And so it's very often that it's amazing how the mistakes can turn into like positives. But then this turns into another critical thing, is that not just do I want to be able to have things run in time with each other like they were, I want to be able to bring them back in time. So if I break it and then start it again, you fix it, don't I? You're not quite in time with each other annoying, so let's break it again. I can actually tell this live loop to synchronize with the through live loop. So when it starts, it's in time. So this is another thing. So not only is it important to be able to deal with errors, and so concurrency gives you the ability to have, you're not going to make mistakes on everything at once, so don't modify them all at the same time, otherwise that's risky. And when you do break one, you're not only able to restart it again, but you're able to restart it in time with the existing ones. And this is really important, so it comes back into, it clicks in. So this sync foo, super cool technical stuff, which essentially just allows the bar live loop to start when the foo live loop is in time with it. And so that's what you need to know. It's a bit like in a band, you might have a conductor or something going 3, 2, 1 drums, and 3, 2, 1 bass, and maybe the bass string breaks, and they're like, oh, I've lost it, and the conductor might bring them in again, 3, 2, 1, and off they go again. And so this sync is kind of like that kind of conducting role for the live loops. Yeah, is that fun? Interesting? Question here, yes?
So the two samples in themselves can have their own thing, and then you can change the, like you do with mixing, so you can change the beat within the track, and then synchronize it like that as well, yeah?
So, yeah, you're talking about the two samples. You mean the two live loops, I'm guessing?
Yeah.
Absolutely. So the two live loops are independent musicians. That's the way to think about it. They can have their own tempo. They don't have to be in time with each other. I mean, by default, they all share the same time. That's just a sensible way to start. But you can write, like Steve Reich, for example, made pieces of music where he would have two violin players play the same piece of music, little small repetitive thing, but at just slightly different rates. And this is really tricky for the performers to actually play, because they're trained to perform in time with each other, and this piece required them to perform out of time with each other. And in Sonic Pi, that means I actually have load example Reich phase. We have one of the Steve Reich phases here, and we can see here that here are the notes to play: E4, F sharp 4. This is the melody, and then we have two live loops, one which is playing slightly slower, another one playing slightly faster, and they've got different sleep times. So they won't be in sync. So when we start this, we hear the same notes, but then suddenly they become apart. Then they'll come back in again, but one note shifted off phase. So this kind of thing, the live loops do not need to be in time with each other at all. And you can actually, as you're performing, you can do this kind of trick. You can make the music go off completely weirdly, and then you can bring it back in if you want to as well. All these are optional. You have really amazing control. I haven't got much time to talk about this. I haven't got much time to talk about time. But time is a really powerful thing in Sonic Pi, and I put a lot of effort into making it really expressive. So even though that looks really simple, Sleep 3, it looks like a 10-year-old child's school thing, it's really incredibly powerful. It's not actually what you might... If you're a programmer and you think you know how that works, you probably don't. It's super fun. I've written papers about it, so it's great. Can you choose instruments other than piano? So in Sonic Pi, you have the ability. Let's look at this. So we have play E1. So we didn't look at this. If you know what this means, you can use notes like E, F, F sharp. If that means something to you, you do not need to do this. So if you start in a school and you say, do you need to understand music theory to understand Sonic Pi? That's too much friction. But if that makes sense to you, that's good. That's a very low note. I can change the synthesizer to be one of the many built-in ones. So each of these, this is the one for sampler, but I have lots of different designs for different sounds. And you could, if you know how to do this kind of stuff and synthesis design, you can design your own sounds. And so here, for example, I'm going to use the Prophet sound. And that sounds good if it's a long release. And release is how long the note takes to last for. So if I go for like 8 seconds, maybe I'm going to go for a low note. Maybe I'll change the cut-off to 70. That sounds good, right? And I can do a bit of algebra in there, like -4. So that's E1 down by 4 semitones. So yes, you can. There's a whole bunch of built-in synthesizers to work with that you can play with. And also you have ability to this a bit bigger. To work with a bunch of other stuff, right? So you can also talk MIDI, and so you can send MIDI events to MIDI synthesizers. So if you've got a really fancy synthesizer at home that look like those ones I just showed you, very expensive ones. Often they'll have a cable you can plug into and send MIDI notes from Sonic Pi to them. And instead of saying play, you write word MIDI, and it's all exactly the same. Works the same. You can receive MIDI notes. I'll give an example of that in a moment. You can share the tempo across the network with other computers. So if you have a bunch of people, if you've got like any of you got friends? Because that would be cool. You teach me how to get friends. It'd be great. Get your friends around with their laptops. Open up Sonic Pi, be on your local network, and you can use this link system by pressing the link button to jam together in time. That's super fun. You can also work with audio in and audio out. So you can take a microphone or a guitar or electric violin, and you can plug that into Sonic Pi, and you can use like the reverbs and distortions I was describing. You can also send audio out. Obviously, that's what I'm doing to these speakers. But sometimes you might want to work with systems that have more than 2 speakers. Maybe you have 10 speakers. And so Sonic Pi can talk to all those 10 speakers independently, and you can do all sorts of interesting, fun stuff with that. And then this OSC thing, that's the ability for Sonic Pi to talk over the network to other programs and to other versions of Sonic Pi to send all sorts of information that you might want to coordinate. So you might want to, in your band, say, I have someone who's going to change the current key, or who's going to change the complexity, or whatever it is you want to do. So it's a way for Sonic Pi programs to talk to other Sonic Pi programs. So again, there's weeks worth of stuff to cover here. It's really fun and really in depth, and it's just I'm showing you there that it's available. But yes, any more questions? Yes. Can you loop something a certain amount of times? Absolutely. Traditionally, that's called iteration. And in Sonic Pi, say we want to do like let's do like play. Let's do something more fun. E1, E2, E4. Say I'm going to choose one of those notes randomly, and I'm going to sleep for a short amount of time. And so maybe I want to do this 8 times. Yeah, again, we have our do and we have our end, where it starts and finishes. And maybe instead of using like E2, E3, E4, I'm going to use like a scale. Like E3 minor pentatonic. Oh, I'm going to mess that up. Scale, E3 minor pentatonic. Why is it doing that? Sorry. Ah, okay, there's an interesting bug. Let's type it out. There we are. There we are. We can do it 4 times or 16 times. And you can wrap that iteration around any code, and it'll repeat whatever that is, that number of times. So yes, absolutely. So this is more useful within a live loop if you want to do something multiple times per beat, or in your compositions, you might want to have certain structures be repeated 3 times, and like just do the verse twice and the melody 3 times, and the verse another 2 times. So you can totally do that. Yeah. Any more questions? Yeah.
If you're performing and you do something very creative and amazing, is there a way of capturing the logging and rerunning that again?
If you're performing and do something you're happy with.
If you accidentally come across a nice melody for me as you're changing it live, is that logging side on the right hand side that somebody can capture and say, oh, that was great, I'm going to run that again?
That's a very good question. Can you capture your performances? I mean, it does have internally a Git history of your commands, but that's really hard to get to use. But I haven't really got a nice way of doing that yet, so you should really capture the code. But the critical thing about Sonic Pi is that all of the code is deterministic, which is a fancy word for saying it does the same thing every time. So even if you're using randomization, all sorts of different things together, that same code will sound the same if you stop it and play it again, or if you email it to your friends. So capturing the code and the algorithmic structures you're using is the current best way to achieve what you're saying. Question?
Can you share like the same program so that 2 people can do things on the same program at once on 2 different computers?
Can you share the program so that 2 people can do the same thing at once on 2 different computers? So the answer is yes, but may not be what you expect. Typically, what you want is, at least I found interesting, is you might want to work with other musicians or friends, and so you don't necessarily want to work on the same thing together, because that could be really confusing. If you can imagine 2 people playing or 3 people playing the same piano, that's going to be really quite tricky. And so, or the 3 people playing the same guitar is going to be quite tricky. So what you probably want to do is you have 3 versions of Sonic Pi running, and then you use the this link system. So you press this magic link button down here, and then suddenly they're all in time with each other. And then you can at that point, you can play together. But if you want to do more coordination, you want to do more automated coordination, then you use that open sound control thing, the OSC thing I briefly mentioned, which lets you send messages between Sonic Pi instances. There's documentation to describe all of that. So that you will then be in control of what it means. Sonic Pi doesn't try and tell you what to do. It just gives you the power for you to do what you want to do. So that's what I would say. It's like you would synchronize in terms of time with this link button, and then if you want more coordination, you'd use this network messages using open sound control. Yeah. Question? Yes?
How do you use a function like this system with abstraction? So if we wanted to play like a specific scale 10 times, we don't have to copy out the 10 times.
Yeah, that's a very good question. So how would you do functions? So Sonic Pi has ability to define a function. Let's play it like this. So I can run this code. It doesn't do anything. It's just now taught the computer that foo is going to play the amplifier, and then it's going to wait a second, and then it's going to play it but at half rate. So now down here I can write the word foo. That's going to play my thing, and then I can then do my, as you mentioned, like let's do that 3 times. So this is a way to, as you're saying, to take a bunch of code that you know you want to use loads and wrap it up into a single word and work with that. There you go. I think I'm running out of time. Any last questions before I finish? No? So thank you so much for listening. Thank you for your time. Thank you for being here at Cambridge Computer Labs. And if you do want to play with Sonic Pi any further in your exciting lives you're going to go away to live, just go and download it. It's totally free. Share it with your friends. If coding music isn't your thing, but you know someone else is interested in learning to code but likes music, this can be a really great way for them to get started, to get involved. We have a really friendly community of artists and performers, which are all talking and sharing their ideas on these forums. So you can go to these forums and ask questions. There's no wrong questions. Everyone's learning. Everyone's doing interesting things. Everyone's happy to share their ideas. And just really, just have fun and recognize that Sonic Pi is hugely creative. Yes? Question? Do we have time for a couple of minutes of demo? Are we got to be kicked out? So, one thing I tend to do is I work with lots of samples I've downloaded and bought. So I have like a nice way of having a shortcut to the names of the locations of the samples, and so then I can work with them. And then I can do quite a live loop. I'm going to do we do that. The lane thing was quite fun. And let's go 4, sleep 8. And then this was use BPM 62. And then you can go into a nightclub mode as well if you want to do this. If I got some examples already that I can just steal now. And I can take 2 and I can work with that with the start of 0.2 and finish at 0.2. So I can work within samples. Create another live loop. Beat. It's a very simple thing, right?
Wrong.